Good morning, all of you. Today we are entering into the second part of the second module. I have posted the problems and its solutions in your classroom. You can verify that and solve the questions for that. In this particular session, we will be getting introduced to what is stochastic process. Just have a brief look at the syllabus. What is stochastic process? What is meant by stationary process? What are the conditions for WSS and SSS? We'll see that in detail. We'll understand what is autocorrelation and power spectral density, and we'll derive the equations for LTI systems with WSS as input. Stochastic process. A stochastic process is any process describing the evolution in time of a random phenomenon. In simple terms, stochastic process means a random process where the process is one variable is time. A stochastic process is a random process which varies according to time. The variable is time. As there is a change in time, you have the other parameters changing accordingly. A sample space composed of functions of time is called as a stochastic process. Stochastic process represent the formal mathematical model for our random signals. Definition of stochastic process. A stochastic process is a set of random variables indexed in time. A stochastic process is a set of random variables indexed in time. The next slide, we will see some examples of stochastic process. There might be questions in your exam about define or what do you understand by stochastic process. Explain with examples. For example, the received signal at the wireless channel output varies randomly with time. The process of this kind is said to be random or stochastic. So you should ensure that stochastic processes are always functions of time and are usually random, in the sense that it is not possible to predict exactly what would be coming next. The outcomes of stochastic process are not predictable. And here what we are going to do is we are going to study in detail about different aspects of stochastic process, mathematical equations, and so on. So let us now study in detail about stochastic processes. Let us consider a random experiment with outcomes observed from some sample space, we call it as S, and events defined on the sample space and the probability of these events. Suppose we assign to each sample point a function in accordance with the rule. What we are doing is that we are creating a random variable, or we are creating a function or a relationship which is going to map every outcome of the experiment to another one particular value. And this rule, what we have studied previously, is nothing but random the random variable. So here is a rule. We have a sample space here and we have denoted it by different outcomes, say S1, S2, S3 and so on. So outcome of the first trial of experiments, second trial S2, third trial S3. So what we'll get is this xi of t will be equal to x of t comma s, where t stands for the time and s is the signal. The outcome of a stochastic process, what we call it as xi of t is equal to x of t comma s. So this is the sample space S, and we are considering different trials S1, S2 and up to Sn, and the outcome of the experiments are given as a stochastic process, and it can be defined as xi of t is equal to a random variable x with, you know that stochastic process always will have one variable as time and the other one as signal. So let us consider the random variable x of t of x to have a time period t, capital T. That means that small t is something that is between minus capital T and plus capital T. Okay, so here this is minus capital T and plus capital T. This is the range of the stochastic variable. In that case, xi of t, which is a random variable of x with time and signal, will give it to be xi of tk, I is equal to 1 to n, that is equal to random variable of tk si, where I is equal to 1 to n. Okay, so we are considering this to be a periodic function with a time period t. So this is a fundamental equation for a stochastic process. We'll study what is a stationary process next. So a stochastic process is something that varies with time, and stationary process is something that does not vary with time. A random process is said to be stationary if the statistics is not affected by the shift in the time origin. A random process is said to be stationary if it does not get affected by the shift in its time origin. This means that a random process or a stochastic process x of t and x of t plus e, where e is an arbitrary time, will have the same statistical processes. Statistical properties. If a random process is divided into number of time intervals, the various sections of the process exhibit essentially the same statistical properties. Such a process is said to be stationary, and the others are non-stationary. That means that in a stochastic process, if you add an arbitrary value of time to the time variable, what you have to get is the same value, or its statistical properties are not changed. Those kind of processes is known as stationary processes. So now let's consider X to be a random process that is observed in time. That means X is a stochastic process. Fx of T1 be the probability distribution associated with the stochastic function at different samples of time. Okay. Suppose that the random process is observed at time ti plus tau and the corresponding distribution function is fx t1 plus tau of x. Then if fx t1 of x is equal to fx t1 plus tau of x, then this process is called as a stationary process. Stationary process is very important and you may need to check whether a process is stationary or non-stationary. You may be given examples and you may be asked to prove it. So in this stationary process, you can observe that the probability distribution function fx of t plus tau, that is fx of t1, is equal to fx of t1 plus tau. That means that the probability distribution is independent of time for any value of x. Sorry, any value of t. So this condition applies for all, and for all this we say that is the stationary process of the first order. A first order stationary random process has a distribution function that is independent of time. You could also write it as a stochastic process. Okay. So we'll study the properties of stationary process. First property, fx of x comma t is equal to x is equal to the probability distribution at a different point of time is same as the original for all t and tau, and this is called as the first order distribution function of a stationary random process is independent of time. The first property is that it is independent of time. Independent of time. This is the first order. For the second order, k is equal to 2. We have two time durations t1 and t2. For tau is equal to t minus 1. We have fx of t1 and t2 of x1 and x2 two different time points is equal to fx of 0 t2 minus t1 x1 comma x2, and this is the second order distribution function of the stationary random process. Depends on the time difference between the observation times t1 and t2 and not on the particular times at which the random process is observed. That means in the second order stationary process we consider 2 points of time t1 and t2. Okay, two observation times, and it is not on the absolute time that it depends only upon the, this independent of the difference of times t1 and t2. Are you all able to understand what is this second order distribution function or second order distribution function of a stationary random variable? Next, very important topic, conditions for wide sense stationary and strict sense stationary processes. Please concentrate very well because 80 to 90% there are chances of questions coming from this topic only. So what is a strict sense stationary process and what is a wide sense stationary process is what we'll be looking into. A continuous time random process, which is a stochastic process, is strict sense stationary if the statistics of the process are invariant to a time shift, specifically for any time shift tau and in any value of the distribution function x1 to xn, where the distribution is a function of x1 to xn and the time t1 to tn. So if you add a time variable tau to this particular time intervals, you should not find any change in the distribution function. This kind of stochastic process is called as a strict sense stationary process. A process where you have a time shift and there is no difference in the distribution function. So we'll see what is a wide sense stationary process. A wide sense stationary stochastic process is some random process where the mean function and the autocorrelation function are invariant to the time shift. In a strict sense, the distribution function itself is invariant to the time shift. Here, autocorrelation function and the mean function are invariant to the time shift. That means that mu x of t is equal to a constant and rxx of t, t plus tau is equal to rxx of tau is a function of only the shift in time. So we will be commonly asked questions about, they'll be giving you a random process and asking you to find out whether this particular process is a wide sense stationary random process or not. The two conditions that you have to keep in mind is that the mean function is constant and the autocorrelation function is also invariant to a time shift, what we call it as tau. What is autocorrelation function? We'll be seeing in the coming slides. So come on, any one of you tell me what are the two conditions for a stochastic process to be wide sense stationary? What are the two conditions for a stochastic process to be wide sense stationary? First condition is that the mean function should be constant. Second condition is that the autocorrelation should be invariant or should be same as the change in the time tau. Okay, so these two conditions are extremely important. You need to study this for your exams. You need to check the conditions also. All strict sense stationary random process will be wide sense stationary processes, provided that the mean and the autocorrelation function will be invariant of time. But the other way around, it is not true. All WSS need not be SSS. A wide sense stationary process does not necessarily need to be a stationary process. In the strict sense, we refer to a process that is not WSS as non-stationary. So let us see an example and understand these two conditions in detail. Okay, a random process is said to be stationary in the strict sense if none of its statistics are affected by a shift in its time origin. Okay, now this slide is particularly meant to make you understand the difference between SSS and WSSS. There could be a question, or there was a question in your previous question papers on comparison of two kinds of stationary processes. So a random process is said to be White's and stationary if two of its statistics, just the mean and the autocorrelation, does not vary with the shift in its time origin. Thus, a process is WSS if the mean mu x is a constant and Rx of t comma T1 comma T2 is equal to Rx of T1 minus T2. Autocorrelation function. Okay, we'll see in the next session what is autocorrelation after break.